Hi, everybody. This is John Whitaker for the Probability Graduate Level class, and this is our 12th video lecture. And today we want to continue talking about independence between two random variables, say x and y, look at some examples of those, maybe have some facts about it, about independent random variables. And we also want to look at something called the covariance between two random variables, x and y. And we'll do examples of that after giving the definition and have some facts. Anyway, it's time for us to get started. And today we're going to start with an example. So, as an example, let's let f of x comma y be equal to 1 over 30 x squared y, where x is equal to 1 or 2, and y is equal to 1, 2, or 3. P, the joint PMF of x and y. And so our question here is, are x and y independent random variables? And we had a definition for independent random variables, an alternate definition of random variables. Then we had a fact, it was an if and only a fact, having to do with the PMFs or PDFs of x and y, and independence relationship there. And so we're going to use that fact here. And here's what we're going to have. So the fact I'm referring to is if the PMF, or PDF, in this case PMF, of x times the PMF of y is equal to the joint PMF, then the two random variables had to be independent. And so here, let's start off this question. Let's start off by saying, to note, so we get our solution, that the PMF of x, what that's equal to is the sum over all y values of f of x comma y, the joint, that's the sum over all y values, y running from 1 to 3, of 1 over 30 x squared y. So let me see, what is that equal to? This would be 1 over 30 x squared, and then y is equal to 1, we just have 1, plus 1 over 30 x squared, and then y is equal to 2, we get 2, plus 1 over 30 x squared times 3, and y is equal to 3. So that's 3, 5, 6 of them. So this is 6 over 30 x squared, which equals to x squared over 5. So that is the PMF of x. 1/5 x squared. Okay. Well, now let's look at the PMF of y. We're going to do something similar. That's the sum over all the x values of f of x comma y, which is equal to the sum as x runs from 1 to 2 of 1 over 30 x squared y. Okay, that's equal to, so when x is equal to 1, we have 1 over 30, 1 squared, so that's just 1, y, plus 1 over 30, and then 2 squared is 4, y. So this ends up being 5y over 30, which equals to y over 6. So that's what we get there. So let's note that, that the joint, f of x comma y, which is equal to 1 over 30, x squared y, is equal to, so it's x squared over 5 times y over 6, so that is the same, and that's equal to f of x times f of y of y. So since the joint is equal to the product of each individual PMF, then X and Y as random variables are independent. All right. Let's look at another example where we look at continuous random variables. So let's let f of x comma y, I think this is some example we've got several times before, be 5/16 xy squared if 0 is less than x is less than y is less than 2, and 0 otherwise, p, the joint probability density function of x and y. The question is, are x and y independent? Okay. Well, again, we're going to see if the joint's equal to the product of each individual PDF. So let's first of all note that f sub x of x, in this case, is equal to the integral from minus infinity to infinity of the joint, but done with respect to y. Now here, let us draw the region along the xy plane where the joint is non-zero. So we've seen this example before. We have this square from 2 to 2, and y equal to x cuts this square in half, and the part where x is less than y within this square is this top half. You can check a point to see that, and we've done that before. So it's this region that I want to integrate over. And so when we think of the x values, what happens is the x, they run from 0 to 2. And for a fixed x, what do the y values go from? So well, they go from that line. So that line is from, these are the y values. They go from x to 2. And then here, this is 5/16 xy squared. All right. And then we would have dy. So this ends up being 5/16 x, that's a constant, and then the integral of y squared, antiderivative of y squared with respect to y, is y cubed divided by 3. And we want to evaluate that from x to 2. I'll finish it up over here. Okay. So we stick in 2, see what we get, and subtract that from that, what we get when we stick in x. Let's find another theorem of calculus. So this is 5/48, the 16 times 3, 48. Here when I stick in 2, it's, for y, it's x times 8 minus, when I stick in x for y, I get 5/48. This will be x to the 4. This will simplify, so I think what we end up getting is 5/6 x minus 5/48 x to the 4. Yes, that's what I got before. Note, we look for the PDF of y. We have f sub y of y. It's going to be the integral from minus infinity to infinity of the joint, and when we do the integration with respect to x. Again, the region of integration for where the joint is non-zero is this little region. And so if we fix a y and say what do the x values run from for this non-zero region, they run from 0 to y, and then f of x comma y over that region is 5/16 xy squared, and then we have dx. Okay. So this ends up being antiderivative. It's 5/16 x squared over 2 y is a constant. We're going to have x running from 0 to x running to y. So we stick in y. This is going to be 5/32. When we stick in y, we have y cubed minus, when I stick at 0, we just get 0, so corrects. This ends up being 5/32 y cubed. Okay, so here's what we note. So note f sub x of x times f sub y of y, which is equal to, in this case, let's see, it was 6x minus 5/48, I think x to the 4, times, okay, so times f sub y was 5/32 y to the 4 does not equal to 5/16 xy squared. Okay? They're not the same. And so because they're not the same, thus x and y are not independent. They are dependent random variables. Okay, we'll write up a fact, and then we'll prove the fact. It says, if x and y are independent random variables, and let's call it G and H are functions, so there can be any functions, then the expected value of g of x times h of y is equal to the expected value of g of x times the expected value of h of y. Okay, so that's the fact. Let's prove it. We'll prove it by looking at the two cases that we're interested in. And so, first of all, we'll have the setup. So we'll let x and y be continuous. Not continuous, but be independent random variables. And G and H be two functions. So the cases that we're interested in are where x is X and Y are both discrete or both continuous. We're going to look at, first of all, case 1. Suppose X and Y are continuous. Okay. Then, if we do that, what is the expected value of the quantity g of x times h of y? Okay. This is really the expected value of some function of x and y. We can break it down to g of x times h of y, but this is really some function right here of x and y. And so we had a definition of that. It was the integral from minus infinity to infinity. Integral from minus infinity to infinity of that function, so here it would be g of x times h of y, times the joint, in this case, pdf, dx dy. Well, because of independence, we can break this into, break the PDF into a product of individual PDFs of the joint one. So here we have the integral from minus infinity to infinity, integral from minus infinity to infinity of g of x, h of y, and here it's f sub x of x, f sub y of y, dx dy. Now, what I want to do next is note that h of y and f sub y of y do not have an x in them. And so this inner integral doesn't have, it's being done with respect to x. So the h of y and f sub y of y, they are constants for the inner integral, and I can bring them out. And that's what I'm going to do next. Okay, so that gives the integral from minus infinity to infinity. And then I would have, I pulled out the y, so it's h of y, f sub y of y, integral from minus infinity to infinity of g of x, f sub x of x, dx. So I'll do this first, and then dy. Now, this inner integral is nothing more than the definition of the expected value of g of x. So this is equal to minus infinity, infinity, h sub y, f sub y, y. Here's expected value of g of x, dy. The expected value of g of x is a number. We're assuming that that's finite. This is equal to the expected value of g of x times the integral from minus infinity to infinity, because it was a constant, h of y, oops, times f sub y of y, dy. And then this is nothing more than the definition of the expected value of g of x. I'm sorry, the expected value of h of y, that's what it is. And that's what we were looking to prove in this case. So, that's good. Let me say that case 2 works analogously. And let me write this up. Except instead of integrals, we're going to have sums. I'm not going to do it. I'm just going to write up that statement. Case 2. If or let x and y be discrete. The proof works analogously to the proof in case 1, except we use summations instead of integrals. more than that, to make that statement. The next thing I want to do is give you a definition. And so as I said at the beginning, we're going to look at something called the covariance between x and y. So here's the definition. So we let x and y be two random variables. Then the covariance between x and y is denoted by COV, parentheses, x comma y, and given by the covariance between x and y is equal to, well, it's the expected value of the quantity. All right, so it's x minus the expected value of x, that quantity, times y minus the expected value of y. So that's its definition. Well, that definition is similar to the definition of variance. And you might remember, we often had a formula for variance that we would use. So we had a formula for variance that we often use. And we're going to have a formula for covariance that's going to be helpful in a lot of cases. So let's get that formula as a fact, and then once it's established, we'll calculate some covariance. Okay, so I have this little fuzzy, there we go. So here's the fact. We're going to let x and y be random variables. Then the covariance between x and y, and it's similar to the variance formula, is equal to the expected value of x times y, so it's the expected value of the quantity x times y, minus the expected value of x times the expected value of y. Now, I'm going to show it a little bit later, but if y is the same thing as x, the covariance of x with x, expected value of x times x, that's expected value of x squared, minus expected value of x times expected value of x, that's expected value of x squared. It is the variance of x. Okay, so it's very similar in terms of its formula, okay? Covariance from variance. So here, let us prove this fact. Okay? So we're going to prove this fact general. So here, note the covariance of x with y. Well, what it's equal to is equal to the expected value of the quantity x minus the expected value of x times y minus the expected value of y. And let's multiply that out. Oops. So that's equal to the expected value of the quantity x times y minus x times expected value of y. So minus y times the expected value of x, and then finally plus the expected value of x times the expected value of y. Now, the expected value of subtraction and addition, that's the subtraction or addition between expected values. So this is the expected value of the quantity x times y. That's beautiful. Minus the expected value of x times the expected value of y. Minus the expected value of y times the expected value of x. Plus the expected value of the quantity, the expected value of x times the expected value of y. Now, I want to tell you that we're not going to do anything with this first one. Well, I have room here. I'll put a little bit more. That's left alone. It's important for our formula. Involved in our formula. Now, the expected value of y is a constant. So when you take constant times x and take its expected value. We pull the expected value out, expected value of y out, and that's the expected value of x left. Again, expected value of x is a constant, it can be pulled out, so expected value of x times the expected value of y. And then here, plus, this is the expected value of, well, this is a constant times a constant, so what's here is a constant. Expected value of a constant is that constant, so this is the expected value of x times the expected value of y. Now, I'm going to write down what the end result is. But you'll notice this guy here and this guy here are the same term, and with this one the same term. These two guys will cancel out, we're just left with what we want. So let me write that down. So this is the concluding line. That's equal to the expected value of x times 1 minus the expected value of x times the expected value of y. And that's what we were trying to show. That's what the covariance is. All right, so that concludes the proof. Now let's look at some examples. So here, as an example, we're going to let f of x comma y be equal to 1 if 0 is less than or equal to x, is less than or equal to y, is less than or equal to the square root of 2, and 0 otherwise. Okay. B, the joint PDF of x and y. Okay, so what we want to do is we want to find the covariance between x and y. All right, well, here's what I'll know. The covariance between x and y by our formula is the expected value of x times y minus the expected value of x times the expected value of y. That's what we have. Well, let's look at the region of integration, try to compute each one of those 3 expected values involved to get our numerical answer. Okay, so note the expected value of x times y. Well, over here, let me look at the region of integration. So, what is this guy equal to? This is equal to the double integral from minus infinity to infinity of x times y times f of x comma y dx dy. It needs to be a double integral, okay? Made a mistake. Now, f of x comma y is often 0. So where is it non-zero? Let's look at the region. So if you look at the definition of f of x comma y, the x's and y's run from 0 to square root 2. So this squared. And then we have y equal to x as a function we need to look at, that linear function. And again, we want the part where x is less than y. It's this top triangle we can try to pronounce, and that's what you'll get. It's top region. All right, with that being the case, the y values run from 0 to square root 2. For each one of these y values, the x value, for this particular, the x value will run from 0, let's see, to that line, and in terms of x, that line's equal to x equal to y, so that's y. So x, y, here, f of x comma y is just 1, so dx dy. Excellent. So I need an integrate with respect to x. What do I get? I get integral from 0 to square root 2. Antiderivative for this guy is x squared over 2 times y. The x value runs from 0 to y. And then whatever I get, I integrate that with respect to y. When I let x be y, I'm going to get y cubed, so it's an integral again, from 0 to square root 2 y cubed over 2 minus 0, so I want to write that down, dy. So when I integrate this, I'm going to get antiderivative of y to the 4th over 8, 0, square root of 2. When I stick it in the square root of 2, we'll get square root of 2 raised to the 4th power over 8 minus 0. Square root of 2 times square root of 2 is 2. Times square root of 2 times square root of 2 is another 2. 2 times 2 is 4. We get 4 over 8, which is just 1/2. So that's the expected value of x times y. Now we need to find the expected value of x, and we need to find the expected value of y.
Oops, sorry. Okay.
So the expected value of x, well, that's equal to, you still make it double integral, I will, x times f of x comma y, dx dy. Again, our region of integration here, square root of 2, square root of 2, this box, we're looking at the upper triangle in this case. I can rewrite this again as the integral it was from 0 to the square root of 2, here it was from 0 to y, x times 1, dx dy. Same type of integral. The y values run from 0 to 2 for any particular fixed y values. Those x run from 0 to this line, that's x equal to y. That's why we have these limits. That's equal to the integral from 0 to the square root of 2. Here this will be x squared over 2. Evaluate from 0 to x equal to y, dy. And when we do this, we end up getting the integral from 0 to the square root of 2. It will be y squared over 2 dy. And now when you integrate with respect to y, you get y cubed over 6, 0 square root of 2. And of course, when we stick in the square root of 2, we'll get 2 times square root of 2 over 6, or square root of 2 over 3. And of course, when we get 0, we have nothing. Okay. Now, for the expected value of y, it's similar in that it's from minus infinity to infinity, minus infinity to infinity, y times the joint, and you integrate dx dy, which I'm going to say, using our same limits of integration, 0 square root of 2, 0 to y, here it's going to be y times 1, dx dy. Antiderivative for y with respect to x would just be yx, so I've got to do the integral from 0 to square root of 2. You need to evaluate this as x runs from 0 to x running to y, and then integrate with respect to y. All right, when we let x be y, we end up getting the integral from 0 to square root of 2 of just y times y, so that's y squared, minus, when x is 0, we just get 0, so I'm not going to write that down. Nothing contributed there. Dy. This is y cubed over 3, evaluate from 0 to square root of 2. When I stick it in the square root of 2, we get square root of 2 cubed over 3. That ends up being 2 times square root of 2 over 3. So finally, we're ready to list the numerical value of the covariance for this example. So, the covariance between x and y is, of course, the expected value of x times y minus the expected value of x minus the expected value of y. We have numbers for this. This was 1/2 minus, what was this? I think I still can see it. It's the square root of 2 over 3 times, this was 2 times square root of 2, I think, over 3. And so this ends up being, I think common denominator, this is 9, this 2 is 18. So it's 9 over 18. Here this would be, well, I need to go a little slower for me. this is going to be 4 over 9. So this is equal to, this is 9 over 18 minus 8 over 18. So we end up getting 1 over 18. And that's the answer for this problem. All right, that was a continuous case problem. Let us look at a similar example, but when we're discrete. Here it is. So let's let f of x be equal to x plus y over 21, joint PD, so this should be x comma y equal to that. Where x equals to 1 and 2 and y equals to 1, 2, it's so familiar. Joint PMF of x and y. And so my direction will be find the covariance of x with y. All right, we're going to use that formula again. Okay, so the covariance between x and y by the formula is equal to the expected value of x times y minus the expected value of x times the expected value of y. So we need to find these three expected values for our problem. So note, the expected value of x times y, well, that's going to be a double sum over all x values. Well, I'm going to be a little bit more specific. So x goes from 1 to 2, y goes from 1 to 3. Of the function here of x and y, so it's x times y, times f of x comma y. And let's go ahead and put that in. So that was x plus y over 21. So that's what we have in our particular situation. Let's see. Let's let x be equal to 1 and let y run. So when x is 1, we have x is 1 and y is 1. 1 times 1, so that just be 1. And then here, this is 1 plus 1 over 21. Plus, now when x is 1 and y is 2, we have 1 times 2. And then 1 plus 2 over 21. Plus, here we have 1 times 3 times 1 plus 3 over 21. Now that handles all the parts where x equals 1. Now when x is 2, we have 2 times 1, y is 1. And then this will be 2 plus 1 over 21. Plus, y is 2, so we have 2 times, I'm sorry, x is 2, so 2 times 2, y is 2. And then 2 plus 2 over 21. And then plus, x is 2, so we have 2 times 3, 2 plus 3 over 21. So when we look at this, let's see, this is 2 over 21. This guy right here, I think it's 6 over 21. This guy right here is 12 over 21. I think here this is 6 over 21. Plus, so where am I here? So this is 4, 8, 16 over 21. Plus, this is 6 times 5, I think it's 30 over 21. Okay, so that's 46, 52, 54, 64, 70, I think I get 72 over 21. That can be reduced, and definitely 3 goes into both of these. So 3 goes into 7 2 times, 1 left over, so I think it's 24 and 7s. That's what we get, 24 over 7s. And that's what I got previously. So that's a good sign. Okay, we still need to find the expected value of x, expected value of y, and then we'll be able to compute covariance in terms of this numerical value. Note, the expected value of x, that's the sum over x is going from 1 to 2, sum y is going from 1 to 3 of x times the joint PMF, which is x plus y over 21. And so that's equal to here's what we get. When x is 1, we get 1, and then it will be y is 1. 1 plus 1 over 21 plus x is 1, so we get 1, and y plus 1 plus 2 over 21, so y is 2. And plus 1, and then x plus, 1 plus 3 over 21. That's all the outputs we'll get when x is 1. When x is 2, we get 2, and then 2 plus 1, and y is 1 over 21, plus 2 times 2 plus 2 over 21, plus 2, and then 2 plus 3 over 21. Let's see what these numbers are. So here's 2 over 21, here is 3 over 21, here is 4 over 21, here is 6 over 21, here is 4, it's 8 over 21, I think, and then plus 10 over 21. And when I add these up, it's 18, 24, 28, 31, 33 over 21. And when I reduce that, so 3 will go over both of these, this looks like 11 cents. That's what I got previously. Now, the expected value of y, that's equal to sum as x is run from 1 to 2, sum as y runs from 1 to 3, y times x plus y over 21. And so that's equal to, I'll start it here. So now I'll start here. So let's see, when x is 1, we have, and y will be 1, it will be 1 plus 1 over 21, plus y is 2, 2 times 1 plus 2 over 21, plus y is 3, so it'll be 3, and 1 plus 3 over 21. Plus, when x is 2, we have y equal to 1, so it'll be 1 times 2 plus 1 over 21, plus y is 2, 2 times 2 plus 2 over 21. And then finally, y is 3, and then we have 2 plus 3 over 21. So when I add these together, let's see, this is going to be 2 over 21, I think, plus here it's going to be 3 times 2, it's going to be 6 over 21, I think. There's 4 is 12 over 21, I think. And then this is going to be 3 over 21. I'm running out of room, so I'll finish it up right here. Plus, this is going to be 4, going to be 8 over 21. And then here, what are we going to have? 5, 15 over 21. Okay. Let's see, what is this? It's 2, 8, 20, 23, 31, it's 46 over 21. That's right. So the expected value of y equals to 46 over 21. Thus, when we look at the covariance in this case between x and y, that's equal to expected value of x times y minus the expected value of x times the expected value of y. When I stick in the numbers here, what we're going to get is 24 over 7 minus, and I think it's 11 sevenths times 46 over 21. And when you work with that, I believe you'll get minus 2 over 147. So I'm not going to show those details, but I think that's what you get. All right. The next thing I want to do is list some properties for covariance. So some properties of covariances. Okay, the first one, it's something I've mentioned before, is that the covariance between x and x, that's equal to the variance of x. 2. The covariance between x and y, that's equal to the covariance between y and x. 3. 3 is, if you look at the covariance between Cx and y, that's equal to C times the covariance between x and y. And the fourth property I'll write over here, what it says is the covariance between x and y plus z, that's going to be equal to, it's the covariance of x with y plus the covariance of x with z. So we'll prove all four parts of that. Properties, all four properties we'll prove. They're not hard to prove. Okay, so for one, here's my proof. For one, we're looking at the covariance between x and x, and we want to show it's equal to the variance of x. Well, what's its definition? So not formula, but definition. This is the expected value of the quantity x minus the expected value of x. And then it's got the second random variable involved. So normally we say y, but that's x minus the expected value of x. Well, that's equal to the expected value of x minus the expected value of x to b squared, and that is nothing more than the definition of the variance of x. I'm done. I didn't do it. That's one. How about two? That's very similar. So here, we look at the covariance of x with y, and we want to show that it's the same as the covariance between y and x. Well, what is this? This is the expected value by definition of the quantity. Let's see, it's x minus the expected value of x times y minus the expected value of y. And then, look, this is a multiplication. You take one first times second, the same thing as second times first. So I'll say, hey, this is the same thing as the expected value of y minus the expected value of y times x minus the expected value of x. And so that, by definition, is nothing more than the covariance between y and x. So we're done with that guy. That property. 3, in this property, we want to show that the covariance between Cx and y is equal to C times the covariance between x and y. That's what we're going to show. But here's what I'm going to do. Instead of using the definition, I'm going to use that formula. This is equal to, by formula, is the expected value of the first guy involved, which is Cx, times the second guy, which is y, minus the expected value of the first guy involved, Cx, times the expected value of the second guy involved, which is just y. Now here you can pull constants outside of the expected value, and that's what C is. So C is a constant. So C times the expected value of x times y, minus, here I can pull out that constant, so C times the expected value of x times the expected value of y. And now we have two terms, and as a common factor they have C, so I can pull out the C for both terms, and I'm left with C times the expected value of x times y minus the expected value of x times the expected value of y. But of course, what's in brackets is very easy to recognize as the covariance between x and y. And that's what we were trying to prove. So C times that covariance. We got one more fact to prove. I'll put it up here. Okay, so the fourth one is, note the covariance between x and y plus z. Well, we want to show that's the same thing as the covariance between x and y plus covariance between x and z. Well, by formula, what this is equal to is the expected value of x times y plus z minus expected value, first of which is x, times expected value of y plus z. Now, using properties of expected values that we've already proven, well, I guess I'll distribute it first. So this is expected value of xy plus xz minus expected value of x, and here, this is times, here's a property that I use, this is expected value of y plus the expected value of z. Again, using property of expected value, the expected value of the sum, excuse me, it's the sum of the expected value. So this expected value of x times y plus the expected value of x times z. Here, distributing this minus expected, distributing the expected value of x, we get the expected value of x times the expected value of y minus, again, the expected value of x times the expected value of z. Regrouping this expected value of x times y minus the expected value of x times the expected value of y, and then plus this expected value of x times z minus the expected value of x times the expected value of z. And so this first quantity by formula is nothing more than the covariance between x and y, plus this second part is nothing more by formula than the covariance between x and z, and that's what we set out to prove. We have proven the four properties. Okay, there's one more fact, and I want to prove it, and we'll use it next time. But this fact and its proof will conclude this lecture. So as a fact, it says if x and y are continuous random variables, with the PDF of x being f of x of x, and the PDF of y being f of y of y. And x and y are independent. Then the PDF of x plus y, so that's what we're going to be interested in, the PDF of the sum of independent random variables, is f of x plus y, evaluate something we'll call it a, and that's equal to, and it's going to be in the integral from minus infinity to infinity of f sub x of a minus y, that's right, times f sub y of y dy. That's what we'll get. So we want to prove that. And the way we're going to prove it is by starting off with CDF. So we're talking about continuous random variables. And that are independent. We're adding them. So here's the proof. We're going to let x and y be continuous random variables. continuous random variables that are independent. And the PDF of x is f sub x of x, and the PDF of y is f sub y of y. All right, so here's what I'm thinking. Note the CDF of x plus y is, so it would be big F of x plus y, and let's say a value. And what's that equal to? That's the probability that x plus y is less than or equal to A. What that is a double integral over the region where x plus y is less than or equal to A of the joint f of x, y, dx, dy. Now, let's get a kind of a picture here about this region where x plus y is less than or equal to A. Look, A is maybe here and here, okay, along the x and y axis. Okay? That's x plus y equal to A, and that's what that would be. And if you want to know where x plus y is less than or equal to A, so here, if I take 0 and 0, 0 at this point, we're looking at A here, in this case being positive, then take the point 0, 0, which is in this region below, if you will, this line. It does fit that 0 plus 0 is less than or equal to this positive A. So it's this region we're talking about integrating over. In addition, before I really get to that, I'm going to keep that x plus y being less than or equal to A region listed there. But what I'm going to note is because of independence, the joint is equal to the product of the individual. Now, how do I express this region where the f of x, how do I express this region we want to integrate over? Well, let's see. First of all, if I take a look at the y base, see what they can run from. Well, I mean, it keeps going up. It's way down here to forever. So it's from minus infinity to infinity. Hey, that's part of what we're trying to prove. For a fixed y, this one, where do the x values run from? They run from minus infinity up to this line. What is this line? Well, in terms of x, remember this line is x plus y equals to a. So if I solve for x, that says x equal to a minus y. So I integrate up to a minus y. And here I'm going to have f sub x of x, f sub y of y, and then I have dx dy. Almost done.
And before I leave there, what I want you to notice there is that we have f, we're integrating f sub x of x and f sub y, y with respect to x first. And so the f sub y, y, that is constant, can be considered a constant function with respect to x. So we can pull it out of that
Second integral. So that's what I'm going to do. This is equal to integral from minus infinity to infinity, f sub y of y, integral from minus infinity to, it was a minus y, f sub x of x, dx, dy. Now this is equal to integral from minus infinity to infinity, f sub y of y, and this part right here is nothing more than the probability that y is less than, no, I'm sorry, that x is less than or equal to a minus y. So that's what I'm going to put. It's equal to, well, that is f sub x, the big F, the CDF, of a minus y, okay, and then dy. That's what that inner integral will be replaced by. So, what we have is f sub x plus y of a, the CDF of the addition of x and y, is equal to this integral. if we differentiate with respect to A, this left-hand side, well, we'll get the same thing if we differentiate with respect to A, this right-hand side. Now, this part right here, the derivative of the CDF is nothing more than the PDF. Here, and I'm not going to go into much details or any details about this, we can pull this derivative inside the integral. And so this is equal to the integral from minus infinity to infinity, f sub y of y. And here, this one is the derivative with respect to A of f sub x of A minus 1 dy. And that's equal to, so here's integral from minus infinity to infinity, f sub y of y, and then the derivative of the CDF of x is nothing more than its PDF. So here I have f, little f, so that's a little f, sub x of A minus y, and I'm taking the derivative with respect to A, so by the chain rule, I have to take the derivative of A minus y with respect to A, but that's just 1. And then we have dy. That's what we were trying to prove. So that ends it. What I want to tell you is this right here has a name. It's called the convolution between x and y. Or we could say between f sub x and I'll say f sub x and f sub y. So sometimes people write it that way. Okay, we're going to use that fact next time in our next lecture, but that's enough for us today. Thank you very much for your time and patience.